Before we move on to solving the Schrodinger equation, or I should say looking at the solutions, we won't necessarily solve it ourselves. How well does this model work for an actual molecule? Well, so an actual molecule, we model using something called the Morse potential. And this is a potential energy curve for it, as we stretch the bond of a molecule, what happens to the potential energy. The mathematical form this takes is V as a function of the bond length L is equal to some constant D times 1 minus e to the minus beta L minus L naught, where L naught, and all that squared, where L naught is the normal bond length, and L is how does it change as the bond stretches and compresses, kind of our spring that we've been thinking about. So what I care less about what the actual equation is, and more what it looks like. So if we make a plot of the potential energy versus L, the distance between the nuclei, or the bond length, this will give us an idea of what an actual molecule's potential energy curve looks like. So this is for a diatomic molecule. So when the nuclei are very close to each other, the energy gets very large. The potential energy, right? That once the nuclei get really close, there, and the electrons and the protons are pushing against each other, and so there's a very large potential energy pushing them apart from each other. And then as they move a little bit further apart, we'll reach a place where it reaches a minimum, and this is what we think of as the bond length, sort of the normal bond length of a molecule. And then it'll increase. Again, as it stretches further apart, there's a force that wants them to pull together. But as you get further and further apart, eventually the molecule will break apart. And that's what's represented over here. This would be dissociation out here. Now, the potential energy that we're modeling for harmonic oscillator is basically just a quadratic, right? It's 1/2 kx squared. So if we make a plot of that, we're going to get something that just looks like this. So it won't be as steep on this side. So an actual molecule has a very steep curve here as the nuclei get close to each other, and a very shallow part right here when the molecule starts to dissociate. And that's not present in the harmonic oscillator, right? This doesn't curve this way, and it doesn't get steeper this way, right? It's always 1/2 kx squared. And so this doesn't seem like it'd be a very good model for an actual molecule if it follows something like a Morse potential. But if we look at this part near the minimum here, if we sort of map a quadratic here, you can see that it matches pretty well in this region here. Let me highlight that in a different color. So in this region near the natural bond length of the molecule, this roughly matches a harmonic potential. And so what that means is that when the molecule is sort of at its, when the molecule is near the bottom of this potential curve, the harmonic model works quite well. So if we have a potential energy curve, the Morse potential, near the sort of normal position of the molecule, the harmonic model works well. But as we get away from that potential minimum, it gets worse and worse, right? And so we can add to our model. If we want to correct for the fact that it's not actually harmonic, we can add what are called anharmonic terms to correct for differences. And so that's, if we want to be more accurate, we add those anharmonic terms to correct for differences. And so situations where the harmonic model isn't going to work very well are, for example, if you have a very shallow potential energy curve, which I haven't drawn particularly well, but there's less space here where it matches well. That's a case where you get things that don't match well. Or if you have a normal curve, but your molecule is in these higher energy states, it's not going to match well, right? If the molecule is approaching dissociation, you get a lot of anharmonicity is the term that in the description of the molecule. So it works really well for molecules near their lowest energy states, sort of normal molecules. But as we get to either very weak bonds, something like a hydrogen bond or something like that, the harmonic model doesn't work particularly well. Or if your molecule has very high excited states in terms of vibrations, it doesn't work very well either.